Let's focus on threads. Okay. The first question arises, why do we need multiple threads? So we use threads when we want responsiveness on multiple interfaces. For example, let's say this box is my process, and I might create a thread which is interacting on the with the user on standard input. It's taking care of standard input, whatever information exchange. I might have another thread which is talking on a socket with another socket. So it is often blocked on the socket read. It just gets blocked. So if I have multiple threads, then I can afford blocking, because if I have one thread, then I need to poll at std in and then poll at socket and then keep polling. I cannot sleep and I cannot block. But if I have multiple threads, I can be blocking, which is very good for a CPU utilization. In addition to these two interface threads, I may have maybe a set of worker threads who are actually doing the work. STD in and socket are kind of channels on which messages come or commands come, and they need to be processed. And then I might have a thread pool of worker threads. That's often a architecture chosen in projects, that you have a thread pool of worker threads and you have interface threads. And because you have multiple threads, threads can happily block on a read system call, and nothing bothers. The system is still responsive at all interfaces. So that is the typical use of threads, that when you want to be responsive concurrently on multiple things, it is not necessary that threads increase the amount of data processed per second. They may not increase throughput, but they at least reduce the latency at each interface. All the interfaces are like responsive. The user gets some response on that. They may also increase the throughput if the actual multiprocessors are able to be exploited, and if they run truly parallel, then multiple threads can increase throughput. So the module in question is threading. Then if you just see help threading, it gives you bird's eye view of the entire threading module. So the things of interest, the most important thing of interest is this thread class, which represents one thread. So you can create a thread object, give it appropriate starting function, and you can give it arguments that these are the input to the starting function. And then when you say thread.start, the thread will start executing. And then if some thread want to wait for another thread, it can say thread.join, and it will wait for that other thread to complete. So thread is like the central piece of attraction here. When you run multiple threads, first thing to notice is that each thread will have a stack of its own. So like this thread, for example, it will have its own function called stack. So what will be the starting point? Every thread has to be given one, either a function or a callable object, and it will start there. It will start at that function. So let me call it F1. And then F1 may call further functions, F2, F3, and so on. And this thread may have been given a starting function of F5, and F5 may call more functions, F6, F7. So all the threads, they have a function called stack of their own. If you debug a multi-threaded program in VS Code, and if you put a breakpoint and you look at the function called stack, you can see different threads will have different function called stack. But apart from that, everything is shared. The global variables are shared. If one thread creates an object, the other thread can access it. Or everything else is shared. Only the stack is one per thread, independent, different for each thread. So given that global variables and objects are shared, and if multiple threads attempt to modify the global variables or objects, then naturally race conditions can occur and data may get corrupt. So you have this semaphore. Normally by default, it is a semaphore with value 1. So it behaves like a mutex. And you can have a semaphore with value more than 1 also. And condition variable, often producer consumer kind of problems, or condition variable, the basic concept is one thread can block on a condition that I will wake up when this condition is true. And another thread or multiple threads can signal or notify that condition that it is true, wake up, do the work. So one example could be a producer consumer problem where a consumer blocks on the condition that the queue must be non-empty. Only then I'll wake up. When there is some product to consume, some work to do. Maybe consumer is worker thread and producer is a listener thread. And listener thread creates a message and sends on the queue when some message arrives. So consumer thread blocks on the condition that queue not empty. And when the queue actually becomes not empty, when a producer pushes something into the queue, then the producer can notify that condition and the consumer can wake up. And then you can have all combinations. You might have multiple producers and one consumer. You might have one producer and multiple consumer also. So all kind of things. So these three possibly are worth understanding. Others also, but these are more frequent. Import, help threading, all the details are there of each class. So let's see threading.thread, a little more about that. So when you create a thread, these are the kind of arguments you pass. The most important is this target. Target is the function at which I begin. Okay. And the other two important things are the arguments. You can pass the arguments in positional argument tuples way. You can only give one tuple, or you can give a dictionary for named keyword parameters. Okay. So that way you can give arguments to this function. So target is the starting function, and using one of these args or KW args or both of these, you can pass arguments to that function. And then you have function. You have functions waiting for another thread to finish. Start means start it. So for the way it works is you create a thread object, you pass it the starting function, arguments, everything, and then you say start. You have given all the information already, but start means fire the engine, create a new thread, and invoke it. Let's see a little about Semaphore, taking threading.semaphore. So this is how you create. You create Semaphore is a class. You can create an object of that class by invoking a constructor with one parameter, what is the initial value, which by default is 1. So by default, a Semaphore is in mutex. So the constructor takes only one argument value. And then you can lock it and unlock it. So acquire and release are the calls. Many times you want to block if you are locking. Most systems which are nice to the CPU, they block that I want to take a lock. So if somebody else has taken a lock, I block. Sometimes you want to use polling. So you can say a timeout that block maximum for this much time, then come back. Don't block infinitely. That's like a non-blocking semaphore. So both are supported. Condition variable, as I explained, it is a condition variable, and the prime thing is one thread will wait for the condition. It will be a blocking thing by default. If you want a non-blocking thing or a timed blocking, that block but maximum for 2 seconds, then you can give a timeout that okay, this is the limit of blocking. And the notify, that is like the thing. Notify versus notify all means that sometimes there are multiple threads waiting for a on a condition. Notify all means wake all of them. By default, notify tries to wake one, but there are no guarantees. It can wake more also. You can kind of understand them as a very high level Python wrapper over the basic C thread. So I have created a dummy program. There is a function input person, which is supposed to take details of a person and return it as a tuple, name, age, and country. So it simply asks these three things, name, age, country, and returns a tuple indicating that. So if I run, it says name, age, and country, and it tells me here is the person detail in one object, the object being tuple. Now let's say I want to do two things. I want to take input of a person, and I want to just as a dummy activity, I want to keep saying hello. This highlighted function says hello 5 times. Okay, sleeping 1 second in the middle. So you can sleep using the time module sleep function. You can sleep for a few seconds. And rather that thread sleeps. If there is a multi-threaded system and you call sleep, that thread sleeps. Other threads are keep going. So I have two functions. One says hello 5 times. Another takes input. Both take time. Saying hello takes time because it is sleeping after every hello. And input person takes time because we type slowly. It takes time. And if this function is like this, keep saying hello and p1 equal to input person, naturally it is a serialized thing. First, all the hello will be said, then the input will be taken. But what we are trying to do is we will create this keep saying hello as a separate thread. So one thread will just keep printing hello, 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 and another thread will be taking input. So let me run this sequential thing. So when I run, first keep saying hello has to complete 5 times, and then the other activity begins. So what we want is this keep saying hello and input should happen parallelly. So now we want to make it into threads. So the same thing, we have imported threading. We have the same functions as we had. Okay. And now we want to create a thread. Creating a thread is as simple as that. You create this thread class object. To the constructor, you have to pass parameters. And the most important parameters is the starting function where it begins. So this parameter is like a callable. It can be a function or it can be a object which defines underscore underscore call underscore underscore. We create a thread object in this highlighted line. So now like the gun is loaded. T1 dot start is like pulling the trigger. Now the physically the thread is created and it is started. Okay. So now 20 times it is saying hello and it is asking for input. So let's run it. So let's run. So it is printing. I'm not typing. One thread is keep printing, another thread is waiting. So I can type. The other thread is still keep printing. I can give input. And now the main script has completed, but the other thread is still going on. There is some detail to it when the main script completes, and if all the threads are like background threads, normally they are killed. They can be killed in the middle also. So sometimes you can see a thing that when the main script completes, the hello also stops because it was running in the background or it was running in a background. It's called a daemon thread. You saw that daemon equal to true. So sometimes you might see that when the main thing completes, other threads are killed in the middle, right? Sometimes we want to synchronize the threads. We want to know that when all the threads, all the hellos are spoken, then we do something more. So for that, you have a provision that you can say T1 dot join. If the main wants to wait for all the hellos to be actually spoken before the main script or the main thread, you can hopefully visualize there are two threads. One thread which just started. I mean, one thread, this whole is being executed in the initial program. One thread every process has, and another thread additional created here. So there are two threads happening. So sometimes the main thread wants to wait for the created threads to finish. So you can do t1.join and let me run it now. So I can maybe enter the data. So main script completed, print has come here, but all hellos spoken has not come. All hellos spoken will come when T1 actually finishes. So T1 has to print 20 times. And now it says all hellos spoken. So T1.join, this is a typical coding pattern. When you create multiple threads, typically the main thread waits for all of them to complete before exiting the program. So in this program, you see one additional thing. I'm printing the process ID and the parent process ID in the main script, as well as I'm printing the process ID and the parent process ID in the another thread which we created, T1. So the only point I'm proving is that they are the same. So we are not dealing with multi-process, we are dealing with multi-thread. So process is 14036 and the parent is 3797. Often when you call a start function, you want to pass it some parameters. So I have just changed this keep saying hello to accept a value, and it says hello that value. I pass a value 1, 2, 3, and it keeps saying hello 1, hello 2 based on that value. So how do we pass parameters? So you come to know that you can pass arguments in these two manner. You can give a tuple of positional parameters, or you can give a dictionary of keyword arguments, or both. You can combine both also. So that's what I have done. I have given a tuple having arguments, and this function took just one argument. So I have given a tuple having one argument. This time I'm creating two threads with the same starting function, keep saying hello. So now two threads are saying hello. So thread 1 with argument 1, thread 2 with argument 2. So one will say hello 1, hello 1, hello 1. Other will say hello 2, hello 2, hello 2, and they will each speak 10 times. And the third thread, which is the main, will take the input. So essentially there are three threads, and the main thread creates two more threads, T1 and T2, and the main thread waits for the two threads to complete, and then things finish. So hello 1, hello 2 is being spoken, and if I give the input, and the main is now waiting, and you can do the same thing using KWR. So in the next example, I am passing the same thing, val, but I am passing it in the keyword arguments type, because you know that I can give val as just the positional 10 or 1, 2, and I can say val equal to 1, that dictionary. So here I'm using the dictionary style, KWR, and you can mix, you can have both from, well, so just the same output. And you can mix them. You can have arcs as well as KWR. You can combine them. One little thing I just did here, I printed the dictionary of the thread object, this dict. So let's just see. So target is that function, understandable. It assigns a name to a thread. You can give a explicit name also if you want. Name is one parameter of the constructor. Just like I had target equal to, I can here write name equal to something. If I want to assign my own name, otherwise it will thread 1, thread 2, some name it will give. Whether it's a daemon or not, that's okay. Native ID might be something like pthread underscore create what it returned, or something. Standard input, output, air, those objects. Two important things to notice: underscore args. When it stores that arguments inside the object, it stores as underscore args. And when it stores that dictionary inside it as a instance attribute, it stores an underscore KWR. So these two are sometimes useful when you have a thread object in your hand and you want to know what were the parameters given to it. These two arguments can help you. This is fundamentally the same example as we did T1 equal to create one thread, T2 equal to create another thread. Both are saying hello. This time what we are doing is we are creating 5 threads, and we are putting them in a list of threads. Often when you have to create a thread pool, you cannot write T1 equal to T2 equal to T3 equal to, because there will be a parameter num of threads, and you have to create that number of threads. So then naturally you will have to create a list of thread objects, and in a for loop you want to create threads, and then that thread you push into the list. So that's what this code is doing. This code is in a way creating a thread pool having 5 threads and storing those thread objects in a list so that those threads can be waited for at the very least, if not other operations, but at least one can wait for them to complete. Or maybe I can do anything with that thread. So it creates 5 threads, and this loop waits for all threads to finish. And 5 threads will be running, and everybody will say hello 3 times. The input person I had commented, so maybe that I can run that also. So, and you can see this weird kind of thing. This is what happens when concurrency happens. 2 threads were writing on std out. One wanted to write hello space 1, another wanted to write hello space 2, and it got garbled. This is one example where somebody may say that take a lock, let the input not overlap or interleave. You can also create a thread by subclassing. If you see this help threading.thread, it will say thread class, init is the constructor, run. Run is the routine that when the thread starts, then this run method actually runs. So it is by default provided automatically for you. Run basically simply calls the target function with the args and kw args. So that is what it is saying. The standard run invokes that callable thing which you passed, which is the target, with args and kw args. But you can create your own run method, and this is what you do when you want to create a subclass. Here I have created a class hello printer, which is same thing, keep saying hello. It prints hello. And when I have to create a thread of my own which has to do some functionality, then obviously I have to subclass thread. I am a child of thread. And the most important function I need to write is what action do I do? So I have to create this run function. So my run function is very simple. In a loop, keep saying hello. That's my run function. And to demonstrate that I can access the arguments, whatever you have given while creating the thread. I just printed underscore args and kw args. It is not using them in this sample code, but I have printed that if you give some arguments, the run function can use them. So I have this class hello printer and I have this input person thing. So how do I create a hello printer thread? I create a instance of that class. That's all. Just like how do I create a thread? I create an instance of thread class. So how do I create instance of a hello printer thread? I create an instance of hello printer class. And then I have to obviously invoke. I do it in the same way, start. When I subclass, I'm still a thread. So other things apply, t1.start, t1.join. Everything you could have done on thread, you can do on hello printer because hello printer is a thread. So everything else it inherits. Only the run, it overrides that do my thing. This time I have not passed kwargs args. We will soon see when we pass it, we will print those values. So let's run. So it keeps saying hello and let me, okay. And args and kwargs are empty because they were not passed, but I could access them. This is just saying that they are the same process that we believe it is multi-threading and not multi-processing right now. You can do multi-processing. There are fork and exec, but right now we are doing multi-threading. Let's pass arguments for the sake of demonstrating that these arguments can be utilized by run. So you can see that these args and kw args were available to run. So this is a powerful alternative. If you want to create every thread as a proper class, then you can subclass a thread. So it makes it very kind of clean, and if there is some thread specific information you want to store, you can have instance attribute, because the run is like the minimal thing you have to have in the class. You can have more. So we have this threading module. Later we will see that there is a multi-processing module also, which allows you to create process. Threading module was allowing you to create a thread. It introduced thread as an abstraction. Multi-processing will introduce a process as a class, and you can create processes, and ultimately it will be calling fork system call within it, but you get the abstraction of a process. At a even higher level, you have an abstraction called futures, and you have a abstraction called concurrent. What it basically means is that you want to submit certain tasks, and those tasks will complete in future. So concurrency, there is a module called concurrent, which says that if you want to do things concurrently, use this module, and there is a concept of a future. We will see what it is, but future means I will submit a task which will give result in the future. And this concurrency can be achieved using two alternatives, multi-threading or multi-processing. And this concurrent module supports both. You can say that using multi-threading achieve these two tasks, or you can say that using multi-processing achieve these tasks. There is this nice tutorial launching parallel tasks, and tasks may be physically realized using threads or processes. So you have the concept of a thread pool executor or process pool executor. You might have a set of threads, a thread pool executing those tasks, or a set of processes executing. When you say executor, that's like a abstract class. Here I'm not saying whether it's a thread based or process based. That's why it is being termed as an abstract class. But the actual things which happen, they happen by either a thread pool executor or a process pool executor. If you just see what is there in the futures, there are these executor entities, thread pool and process pool, which inherit from the abstract class executor. And there is a concept of a future. Future is a task which will complete in future. So we have the same old function, keep saying hello. And then how do we create a pool and how do we run? We run in this manner. So we say concurrent.futures.thread pool executor. We need to tell which pool we are using. You need to say thread pool or process pool. So I right now thread pool. So taking this thread pool executor, and what do we do to the thread pool, or the what do we do to the executor? To the executor, we assign tasks, we submit tasks that do this task, do that task. So the model is simple. You create an executor object, and executor object has a team of threads or processes with it, and then you submit tasks, and it will assign those tasks to either of the threads or the processes. So you can submit these two tasks. So now two threads will be saying hello, and one will be saying hello one will be saying hello two. So let's run. And you can see they are saying hello one two. And there is a parameter max workers. Max workers means, because when you have a thread pool, then all the threads in that pool are worker threads. So how many workers do you want? So if you say I want max workers as two, then practically you get the same output because only two were required and you have two. But if you say that I have a max worker as one, that means what you are saying is that only one thread in the pool. So if you submit a task to that thread, only after that task is completed, the thread will be free. Only then the next task can be completed. So if you say max workers equal to one, then you will peculiarly see that initially the first task gets completed, one is completed 5 times, then the second task two starts. So this is the beauty of this executor abstraction, that if you want to change your architecture from a multi-process to a multi-thread, All you need to do is just a little change here. You can write process instead of thread and you are done. Maybe let me demonstrate that. Let's say, let me print this PID and PPID and let me have two because with one nothing works. Let me have two and right now I'm saying process pool executor. So you can see that there are two processes 5884, 5883 and then they are saying and it is kind of garbled. So that's process pool executor and you can see those two are two processes, sibling processes of the same parent. It's as if this Jupyter, that kernel which was running, which is receiving these commands, is the parent, and then two threads were created. And now let me change it to thread. So now the process ID I should see the same because they will be different threads but same process. Process ID is same, and then still they are interleaved in some. So this is the even more abstraction because at the lowest level you know that a pthread underscore create or fork is the way to create a thread or process. Then you saw the abstraction thread in the threading module. Concurrent is taking it to even high that it's kind of giving an abstraction of a thread pool executor or process pool executor and you submit tasks. So it is like making it even more convenient. You don't have to call create a thread object. You don't have to call sub start on it. It's like giving a ready-made thread pool functionality. The first part is very similar, except we are not submitting one at a time. We are submitting in a for loop. And that loop we have written in the list comprehension style. We could have written a for loop also for x in range 1, 5, this thing. But we use the list comprehension style. The other important thing to note here is that the submit returns something. It returns a future object. So here we are creating a list of futures just in one go. If I had to write it in the other way, I would have written for x in this thing column, next line, F1 equal to executed or submit. So I got F1 in my hand. And then that F1, which is a future object, I could have append in the list F. So traditional for loop, you can do like that. But what is a future object? So when you submit a task, you get a future object which will have the latest status of the task in progress. And when the task completes, it will have the result also. Result means if this keeps saying hello, returns something, then I can access it using the future object. Whatever the return value is, I can access using the future object. Because when I submit a task, I cannot say all done and great. I need to get some result. I need to keep an eye. Did it complete? Did it not? What was the result? So that's the future object. And then there are different ways to deal with the future object. But one is that you can have a such kind of loop that as they complete, you print the result. So as completed, you can understand that it as a iterable, which will keep returning things as they complete. So it is running them and it is printing the result. And notice one line has been added in the keep saying hello that they return a result. This result is the result of that future object, that what that function returned. So let me run that. They are doing the thing and the result is being printed. So there were how many threads? 4 threads. And results are 100, 200, 300, 400. So that makes sense. We will not go much in syntax of this. You can refer the manuals, but you can take away this concept that when you submit, you get a future, and on the future, you can seek the result. If the result is not complete, you need to see what the result will be, but it is very safe to access the result after they are completed at least. So submit creates one task. Now map creates one task for each item of the list. For example, let's say you want to create this, launch this, keep saying hello for every item of a list, then you can use map. So what is map? Before going to executor.map, let's see plain vanilla map. So map basically means that apply this function on each element. So what is this function? It is computing square. So if you do the map, you get square of each element. Okay. Now let's see the executor.map. Executor.map basically is saying this is the function, apply it on each of this. Basically, what it will do is it will create as many tasks as elements in this arg list. So arg list has right now five elements. So it will create 5 tasks. So and it will execute, and then you can print it. Let me run it just like that. So they are running, and finally I get those value *100, those kind of outputs. And I can play around with here also. I can say max workers equal to 1. I'm taking the extreme case that only one task at a time. So the task 5 is happening first, and then hello 1, then 2, then 3. But you can see that they are not interleaved. The one who was printing 5 happened in one shot, then came 1, then came 2, but no interleaving. So only one task is happening at a time. So in multiprocessing, if you just, we are not seeing all of it, but if you see, you have this abstraction called process. Instead of thread, you have process abstraction. You again have condition variables, you again have logs, you have 5, which perhaps is the between processes communication. So we are not going there. You have semaphore, because some semaphores are like within process for multiple threads, but you can have different across process semaphores also. So you have that. We are not going there, but we are just noticing the acknowledgement that multiprocessing also is a area uh, running on both the hardware as well as the software attributes. Platform module can help you.